Hi folks, today we're going to discuss the article entitled A Path Towards Autonomous Machine Learning, otherwise known as the JEPA article by Jan LeCun. This is an article that was published on June 27, 2022. It's been cited 573 times. Let's begin. To understand this article, we're going to start with the concept of associationism and the world as we know it. Associationism is the theory that complex mental processes such as thinking, learning, and memory can be wholly or mainly explained by associative links formed between ideas according to specific laws. Let me provide an example. Imagine that you have a coffee cup and there's an associated idea of heat. Further, you can have the idea of LeBron James, and the associated idea of basketball. These are examples of strong associations. But you can also have weak associations, such as between, say, Ted McCullough and basketball. All this leads to the point that the inherent structure of data about the world is really just a collection of strong and weak associations between ideas. This begs the question then of how to represent these associations. For example, would you use a big table? Could you have a big table that contains combinations of, for example, idea X and idea Y, say, for example, coffee cup and hot, or LeBron James and basketball? You could do this, but the problem is that the table would have to be massive because it'd have to capture all the associations in the world. Second of all, this table would likely be unsearchable because it would take way too long to search for your particular target association. Could you do a probabilistic approach, such as, for example, using LLMs to show associations between, for example, X and Y? Yeah, you could do that. And some features of these LLMs is they represent associations at the letter, word, or sentence or paragraph level and so on. And they're really just powerful association machines where associations are based upon strengths of associations as a statistical matter. Current machine learning, however, lacks the ability to engage in abstract planning. Let me explain what I mean. If you look at LLMs, for example, one limit on them is that there's no model of the world. Rather, the world for LLMs is just seen as strong and weak associations of data. Further, planning for LLMs, to the extent they exist, is limited to historical associations of data without the ability to abstract these ideas in the human sense. This has led some commentators, such as Stuart Russell, to say that at present, however, all existing methods for hierarchical planning rely on human-generated hierarchy of abstract and concrete actions, and we do not yet understand how such hierarchies can be learned from experience. Jan LeCun basically also points out that current machine learning really lacks what he construes as common sense, and that this is also a limitation on current machine learning. For the purposes of this presentation, we're going to focus, though, however, on this lack of abstract planning, because it's this lack of abstract planning that really LeCun attempts to solve with the JEPA architecture. Now, I've pointed out that current machine learning lacks the ability to engage in abstract planning. Well, one question you may have is, well, what about like self-driving cars? Don't they engage in planning to get from point A to point B? And in doing so, manifest abstract planning? Not really. Self-driving cars use largely a trial and error based reasoning learned from past experience, leveraging what is known as model-free reinforcement learning. Further, this trial and error approach is really sample inefficient, as it can take hundreds of hours of training to learn basic tasks that humans can develop in a few hours. And what's more is that this approach doesn't really maintain a model of the world, as it's too complex and costly to do so. If they did, it would be known as model-based reinforcement learning. So to address this problem of a lack of ability to engage in abstract planning on the part of modern machine learning, LeCun proposes a system architecture for autonomous intelligence. While one could easily do several presentations on each one of these modules, I'm going to focus on the world module. That said, let me provide a brief overview of the system architecture. First, there is a configurator module that takes input from all other modules and configures them to perform the task at hand. Then there's a perception module that estimates the current state of the world. There's a world module that predicts possible future world states as a function of imagined action sequences proposed by the actor. There's a cost module that computes a single scalar output called energy that measures the level of discomfort of an agent. There's a short-term memory module that keeps track of the current and predicted world states and associated intrinsic costs. And there's an actor module that computes proposals for action sequences. Within the world module, you have a base architecture for JEPA. JEPA stands for Joint Embedding Predictive Architecture. Let me walk you through the various submodules that make up the JEPA base architecture. First, you have a pair or a joint embedding in the form of input X and input Y. These may be the same or different types of data. For example, X may be an audio data, whereas Y may be video data, they may be text data, but they don't have to be the same types. Next, an encoder X basically takes X and represents it as a state X. Similarly, encoder Y takes Y and represents it as a state Y. State X then is provided to a prediction module that then helps to determine the state Y from the state X with the help of a latent variable Z. Z really is just can be thought of as the plausibility of a prediction as to the association between X and Y. Further, you have a D module that minimizes the error between the predicted state and the actual state. Key to JEPA, though, is that it performs predictions in representation space and doesn't need basically every detail of Y to enable a prediction. And it does so through eliminating irrelevant details by encoders. We're going to get into this more in some of the subsequent slides. In the previous slide, we talked about the base architecture for JEPA, but that base architecture really doesn't enable you to engage in abstract planning. It's really only with the advent of hierarchical JEPA or HJEPA that you see the ability to do abstract planning. Now, a few things about HJEPA. First is that there's kind of two parts to the HJEPA architecture. There's JEPA 1, also known as Module 1, that really produces reactive behavior. So this is behavior with little or no planning involved necessarily. Next, you have JEPA 2 or Module 2 that effectively sits on top of JEPA 1. And note, you can have additional layers of JEPA 2. It's not just limited to one layer of JEPA 2, but you could have additional ones, each one performing more and more abstract planning and more coarse representations of kind of future planning or what have you. So to play this through a little bit, when you have HJEPA, then the prediction module for JEPA 2 does a few things. It estimates missing information about the state of the world and predicts plausible future states. And then you have a regularizer, which is regularized learning, which we'll get into in the next couple slides, that basically helps to create the latent variables to show the associations between inputs X and inputs Y as a part of the estimations that the prediction module engages in. We'll again talk about these various concepts in the next few slides. So HJEPA is really a world model solution to the lack of abstract planning that we see in current modern machine learning. What are some features of HJEPA? First is that it maintains a world model to be used to facilitate reactive problem solving in the form of mode 1 in JEPA, and problem solving that requires abstract planning in the form of mode 2 in JEPA, and to learn from such planning. Further, it uses regularization as opposed to contrastive learning, common to many types of machine learning, as is very sample efficient, has the benefit of addressing the cursive dimensionality and reducing mode collapse. Further, it leverages an energy-based approach to representing the association of abstract ideas, say, for example, X and Y, where strong association is low energy and weak association is high energy. And finally, it has goal attainment like reinforcement learning and uses model-based predictive control to control the actions of agents implementing JEPA. We're going to go through each of these features in the next few slides. So how do you go from mode 2 learning to mode 1 learning? According to the JEPA article, the system is run on mode 2, producing an optimal action sequence. Then the parameters of the policy module are updated to minimize the divergence measure between its output and optimal action at time D. This is a lot, so let me kind of break this down for you a little bit. So imagine that you're kind of engaging in abstract planning and that you're going to grab a coffee cup. So the predicted action is you're going to grab a coffee cup. But when you actually do it, let's say, surprise, the coffee cup is hot, you get burned. So what you want to do is basically minimize the difference between the predicted action and the actual action. And to do that, you'll maybe update basically mode 1 through that prior experience in mode 2 to reduce the difference between an anticipated experience and actual experience. So maybe you'll grab the coffee cup this time using a hot pad so that you're not surprised. Another feature of JEPA is regularized training. What is that all about? Well, According to the JEPA article, a considerable advantage of JEPA is that it can choose to ignore details of inputs that are not easily predictable. What does that mean? Well, one way to learn what something is, even in the case of machine learning, is to learn what it is and what it is not at the same time. And this is known as contrastive training. So for example, imagine you have a number of photos of cats. You would learn not only the features of the cat, but also the background to contrast the features of the cat against. The disadvantage of this is that because you're learning what something is and isn't, the number of samples that you need for training can grow exponentially. A more efficient approach, and the approach proposed in the JEPA article, is what is known as regularized training, where you basically only learn what something is. So again, using examples of photos of cats, you would just learn basically about the features of the cat and ignore the background details. And you would do this using not only X and Y, but you would also use Z as a latent variable that will show the strength of association or not between X and Y. The advantage of this regularized training is that it avoids what's known as the curse of dimensionality. Put another way, that using the contrastive example, there's so many samples that are used that the amount of training that you would have to do goes up exponentially. So regularized training avoids this curse of dimensionality. Further, it reduces the possibility of mode collapse. Mode collapse is where basically photos of, say, the cat will kind of center around, from a data distribution perspective, one image of a cat as opposed to multiple images of a cat. So put another way, JEPA using regularized training is very, very efficient and can ignore insignificant details. Another feature of JEPA is an energy-based approach to understanding regularization and the association between ideas. Let me explain what this means. So with JEPA, it takes a low energy approach to show the association between ideas, meaning that lower energy means stronger associations. Further, as to the relationship between, say, X and Y, strong associations are low energy, having good normative values. So in particular, what LeCun basically is saying here is that where there's a strong association between ideas, that could be represented as, for example, one feeling good, which is low energy, as opposed to, say, for example, high energy, which would be exemplified by, say, for example, hunger or something else. Next, with JEPA, you have a relationship between X and Y as facilitated by Z. So Z is really an unseen association between X and Y. So what's that all about? So imagine that you have basically a video clip of a car approaching a fork in the road, and say that XSX and SY represent possible past and future positions, orientations of the vehicle, etc. And in doing so, you can kind of ignore irrelevant details, background ideals, because again, you're using regularization and not contrastive training. And Z may be really kind of a binary decision. In other words, do you turn left or do you turn right with a car? So again, Z is that unseen variable that helps determine association between past and future actions. Finally, really kind of the goal is to engage in energy minimization. That is to find stronger associations that are then low energy between ideas. And that's really the goal. So as LeCun says, this type of planning through simulation and optimization may constitute the kind of reasoning that most frequently you see in natural intelligence. Another feature of HJEPA is Model Based Predictive Control, or MPC. According to LeCun, the second mode, mode 2, involves reasoning and planning through the world model and the cost. It is akin to model predictive control, a classic planning and reasoning paradigm in optimal control and robotics. Well, what's this all about? Well, imagine that you're driving a car, and in such case, the driver may look at the road ahead of him and takes into account the present state and the previous actions to predict his actions up to some distance ahead, which we'll refer to as a prediction horizon. Basically, the idea here is that you'll have a way to control agents implementing HJEPA that utilizes incremental goals and objectives based upon a defined horizon. This is compared to, for example, classic reinforcement learning, where the solution concept or ultimate reward constitutes the horizon. So through using MPC, you can exert much more control because you're using a limited horizon, whereas classic reinforcement learning, there is no such ability to engage in control of the agent at such a high level of granularity. This procedure is essentially what is known as MPC with the receding horizons in optimal control literature. Summing it up, associationism is a common way to explain how ideas relate to one another, as there can be strong or weak associations between ideas, and these associations can be used to explain the structure of the world. Transformer-based AI, aka LLMs, are really just powerful associative machines that can show associations on a letter, word, sentence, and so on level. LLMs, however, are incapable of abstract planning the way that humans can engage in such planning. HJEPA, a type of JEPA, is capable of abstract planning and learning from such planning through an architecture that facilitates both reactive behavior in the case of JEPA 1/Mode 1 and long-term planning behavior in the case of JEPA 2 Mode 2. JEPA leverages features such as regularization, energy-based approach to understanding the association of ideas, and model-based predictive control. I hope you've enjoyed this presentation.